Hello, everyone. Welcome to the VaNTAGE seminar. And we're continuing a series of talks on profinite groups and Galois theory. And today we're really happy to have Michael Larsen, who's talking to us about the inverse Galois problem for pro-P groups. And Michael, is it all right if we record this talk?
Yeah, that's fine.
Wonderful. And if you have questions, feel free to ask them either in the chat or by raising your hand or in the talk. Michael, please go ahead.
Okay, well, thank you very much for the invitation. It's really a pleasure to be here, even remotely. Yeah, so I want to talk about some work that I did with, let's see, Farshid Hajir and Christian Mayer and Ravi Ramakrishna about the inverse Galois problem for pro-P groups. Let me start very briefly with the inverse Galois problem. I know that there was a talk in this seminar a couple of years ago on exactly this topic in detail, and I'll be very brief. The sort of standard inverse Galois problem concerns Galois extensions of Q. You want to say that every finite group can be realized up to isomorphism as the Galois group of a finite Galois extension of Q. And at one extreme, this is a question about finite simple groups. And that's, I mean, I guess, starting with the alternating groups, that's, if I understand the history, that's how Hilbert came to develop Hilbert irreducibility. And there's, of course, a method of rigid triples by Thompson and others, which has enabled us to solve the problem for all but one finite simple group. I think that M23 is the only one where it's still open. And lots of classes of finite simple groups using various methods, including Galois representation methods, where Galois representations could come from either motives or automorphic forms. There's a bunch of different techniques which have been used, and but that's not the end of the problem that I want to talk about. I'm more interested in the easy end of the problem, which is which starts with abelian groups and then nilpotent groups and solvable groups. The inverse Galois problem is known to have a positive solution for solvable groups thanks to Shafarevich's work. But there's an older paper, which is due to Schultz and Reichart. So they say let P be greater than or equal to 3. Every P group is a Galois group. Over Q. And I want to say a few words about how this theorem was proved. Certainly not the whole proof, because basically our work can be thought of as a profinite version of this theorem, and the proof sort of is structurally similar, although there are some new twists you have to introduce to deal with the infinite case. So what is the idea? The idea is that if you have a P group, say GP, it will always have a central subgroup isomorphic to Z mod P. And then you can look at the quotient called GP bar. And what we would like to do is we'd like to prove this theorem inductively. We'd like to start off with GQ be the Galois group of Q. We'd like to start off with a surjective homomorphism, continuous homomorphism from GQ to GP bar. And we'd like to lift it to a surjective homomorphism to GP. And so the way that you sort of think about doing this is the following. So this extension is encoded in a cohomology class in H2 of GP bar with coefficients in Z mod P. Call that class alpha. So if we have this map F, we can take F upper star of alpha. And the obstruction to lifting to a map from GQ to GP is this F upper star of alpha. If that's 0, then we can lift and then worry about the question of whether it's surjective. I mean, there's some little things to worry about, but basically you want to arrange matters such that F star of alpha is equal to 0, and then you can lift. But then there's more than one way to lift, and the lifts are classified. Well, they form a torsor under H1 of GQ with coefficients in Z mod PC. And so, I mean, what we want to do is we want to lift in some way, and then we want to, as it were, correct the lift using an element of H1 to make sure that we aren't blocked when we come to do the next step. So I want to point out that there are situations, very easy situations, in which there simply is no way of carrying out the lifting. Let me mention kind of a trivial example. So if you think about Z mod 4 as an extension of Z mod 2 by Z mod 2, then this lifting problem amounts to the question: you have some quadratic extension, of Q, let's call it Q square root of 3, and you want to know whether there's some cyclic degree 4 extension which contains the square root of 3. And the answer in this case is no, there is no such extension. If we looked at square root of 5, or indeed look at any number which is the sum of two squares in Q, then there is a way of lifting, but in general there isn't. And so you have to sort of plan ahead to make sure that your lift is not going to be obstructed. And as part of the planning process, I mean, this H1 is an infinite dimensional vector space. We don't allow, in fact, we don't use the full H1, but what we do is we introduce one additional prime. So, I mean, the map F is ramified in a finite set of primes, and we allow one additional prime to ramify. And that gives us enough freedom to make the lift do what we want it to do. Of course, if we iterate this process, every time we turn the crank, we get one additional ramified prime. And in fact, when we do this in the Pro-P case, what we're going to find is that the extensions that we get are almost certainly ramified at infinitely many primes. They don't look like the kind of Galois representations that you would get from geometry. Okay, so I guess that's the main thing that I want to say. One additional point is that this construction will give us tamely ramified homomorphisms. That is to say that when we introduce a new prime in this construction, the new prime we introduce is never P itself. We always introduce primes, in fact, which are congruent to 1 mod P. That turns out to be important. Okay, so much for Schultz-Reichart. Now let me just quickly remind you of the story about Pro-P groups. So a Pro-P group is an inverse limit of finite P groups, just as a profinite group is an inverse limit of arbitrary finite groups. And in fact, a Pro-P group, of course, is a special kind of P group. It's characterized by the fact that the quotient by any open normal subgroup is, of course, a P group. Another way of thinking about what's special about Pro-P groups is that if you have an element in a Pro-P group and you put it to the pth power, call it x to the p, x to the p squared, and so on, this sequence will go to the identity as the power of p goes to infinity. And so this enables you to put elements in a Pro-P group to any p-adic integral power. Okay, so that's what a Pro-P group is. So what are examples? Of course, the standard example is the p-adic integers under addition. That's one example. And another example, a class of examples really, are the so-called p-adic analytic groups. Well, I mean, ZP is a p-adic analytic group, but this is a much more general construction. So what are p-adic analytic groups? So these are groups which um, are, as it were, Lie groups in the sense of p-adic analytic spaces rather than in the sense of real analytic or complex analytic spaces. Concretely, they are closed subgroups of GLN ZP for some n. That's what makes a group p-adic analytic. A p-adic analytic group need not be a pro-p group, but it will be virtually pro-p. That is to say, it will have a, just like what happens with GLN of ZP, if you take the elements which are congruent to 1, the matrices which are congruent to 1 mod p, that forms a pro-p group. A third class would be closed subgroups of GLN, sort of the characteristic P version. Take power series in one variable over FP, and you look at closed subgroups of GLN of this. You could, by the way, do something more complicated. I mean, you could take something like ZP bracket bracket T, or have several variables and so on. But anyway, this 3 is an example which is of interest. And in fact, both 2 and 3 give important special cases of what are called just infinite pro-p groups. So these are pro-p groups which have the property that if you take an open normal subgroup and you take the quotient, well, if you take a non-trivial open normal subgroup and you take the quotient, it'll be finite. So it's like there's no interesting infinite quotients. So if you start off with, okay, I mean, it's not true that all the examples of type 2 or 3 would be of this kind, but so an example of just infinite pro-p group would be something like, let's call it SL1 of ZP. So matrices, n by n matrices of determinant 1, which are congruent to 1 mod p. So this is an example, and instead of using SLN, I could use some other simple algebraic group. And instead of using ZP, I could use the ring of integers in any local field with residue characteristic p. So I could do the examples of type 3. But there are other kinds of infinite pro-p groups besides those which come from 2 and 3. So another example of just infinite pro-p group is what's called the Nottingham group. So the Nottingham group consists of sums of the form t plus an t to the n, an and fp, where the operation is composition. So these power series you can compose. Okay, there are other kinds as well, which classification is not really known. But you see, I mean, in a certain sense, we can think of these just infinite groups as being kind of like the simple objects in this category. That is to say, I mean, okay, I mean, it's not exactly clear what we mean, but it's like they sort of have just one interesting pro-p piece. The other stuff is just finite. And so the kinds of questions that I'd like to answer is, so I mean, the big question is which pro-p groups are Galois groups over Q. And unlike in the case of finite groups where we think we know the answer, as far as I know, nobody really knows, really has a picture of what the answer should look like. Let me just give you a very simple example of one which isn't a Galois group over Q to make you realize that there is something to think about. So non-example is ZP squared, right? I mean, we understand by the Kronecker-Weber theorem exactly what the abelian extensions of Q look like. And there's only one ZP extension of Q, and so you're not going to be able to get ZP squared as a quotient. So I mean, this is sort of maybe you would say a sort of stupid example, but still it is an example, and it shows you have to think about these things. I will say something about a partial example later in the talk. I mean, you'll see in what sense it's a partial example. Okay, so that's the second half of the title, and now I want to explain the simplification that I want to use in thinking about the problem, which is so we assume assume henceforth that there is no ramification at P. So in other words, we are really only interested in the tame case. Again, this is very much unlike the story of Galois representations, where if you're taking a p-adic Galois representation, you expect very interesting ramification at P. So we're assuming no ramification at P. So we're really dealing with any ramification must be at a prime Q, which is not equal to P. So the representation, the restriction to the Galois group of the q-adic numbers factors through the tame Galois group. And since we're talking about a homomorphism to a pro-P group, what we can do is we can take the tame Galois group and we can take its maximal pro-P quotient. So the maximal pro-P quotient of GQ tame is, well, what it looks like is it's a semi-direct product of ZP by ZP. So, I mean, to help you think about this, so let sigma Q be Q Frobenius, and tau Q, a topological generator of tame inertia. And then we have a relation, which is, and I'll never, depending on what we mean by Frobenius, so I'll say this is equal to tau Q to the Q. Okay, so this is the relation between the two generators. We can make, let's see, we want I always have to think about this for a second, the notation for semi-direct product. I guess the normal subgroup is this one, so that's generated by tau, and this one is going to be generated by sigma. So, okay, so I mean, when we're thinking about what these representations are as representations of decomposition groups, we can sort of plan ahead and think about, so if we allow ramification at Q, so we have a map from ZP, semi-direct ZP, to G, the P group that we're trying to So maybe I should have introduced this. So G is going to be a pro-P group, and we're interested in whether G is a Galois group over Q. And if it is, and if it's ramified at Q, then we're going to have a homomorphism like this, where the first ZP is not in the kernel. So tau Q here is going to go to some element here, which is not the identity. So, I mean, one thing we definitely need is, for this to work, what I'll call inertial elements. But what do I mean by an inertial element? I mean, you can sort of see, i.e., elements y not equal to 1, such that there exists x with x, y, x inverse equal to some power of y. Well, okay, I mean, if I'm just trying to define what it means for an element to be inertial, what I'll actually say is that x, y, x inverse, y inverse, I'll say the commutator of x and y, so I don't have to specify what q is, the commutator of x and y is equal to y to some power a, and a will be, in general, can be just taken to be a p-adic number, but what we do want is that a should be congruent to 0 mod p. So this corresponds to the condition which I mentioned before, that I'm going to want q to be congruent to 1 mod p. Q will be 1 mod p in the constructions that we're going to talk about. Okay, so if you want to have any hope at all of realizing G is a Galois group, then not only does G need inertial elements, G needs to be generated. So in fact, G needs to be generated by such elements. Okay, so at this point, let me talk about the condition that we actually need to. So I mean, this is a sufficient condition. It may not be a necessary condition, but we haven't succeeded yet in extending the technique beyond groups of this kind. So in order to explain this, let me define, definition, the P central series of G is defined in the following way. So we define the first term to be equal to G itself. If we were just doing the ordinary central series, we would define Pn plus 1 to be equal to the commutator of Pn and G, where in this profinite setting, the commutator means the closure of the abstract commutator. But what we actually want is to say that this is Pn to the P times this. So in other words, this has the effect that Pn modulo Pn plus 1 is not just abelian, as it would be in the ordinary central series, but it's always an FP vector space. And so we say that G is stably inertially generated if every term in this series, Pn, has inertial elements which generate Pn modulo Pn plus 1, which span this vector space. Okay, so now what is the strategy going to be? So it's going to be an inductive strategy. We're going to look at P mod Pn and P mod Pn plus 1. And Pn mod Pn plus 1, which is, of course, as we've seen, it's a vector space. And in fact, so this is a central extension. And what we're going to want to do is we're going to want to start off with a surjective homomorphism from GQ to P mod Pn. When n is equal to 1, this is a trivial group, so this is trivial. And we're going to want at each stage to lift this to a surjective homomorphism. And again, we're going to have classes. We could define the extension class here to be alpha n in H2 of P mod Pn with coefficients in Pn mod Pn plus 1. And we're going to want at every stage that f upper star of alpha n is trivial. That will allow us to lift. And then lifts are classified by H1 of P mod Pn modulo Pn plus 1. Now, actually, what we're going to do is, I'm oversimplifying slightly. It's actually better to do extensions by one Z mod P at a time. But roughly speaking, this is what we do. And so at each stage, what we want to be able to do is, so we introduce at each stage, we introduce one new ramified prime. And we use a kind of a local global theorem. Haven't entirely described the setup, so I can't justify it. But we use a local global theorem which tells us that we're going to be able to prove the vanishing of so f star of alpha n, of course, lies in H2 of GQ with coefficients in this vector space Pn mod Pn plus 1. But what we really do is we don't look at the full group GQ. We look at the tame part. We look at, okay, yeah. So instead of GQ, we use the maximal extension of Q ramified at primes P1 through Pn plus 1. So at each stage, as I say, we introduce one new prime. And so what we need to know is that that there's a local global principle which tells us that if there's no local obstruction, if the class in H2 vanishes at each decomposition group of the PIs, then in fact it vanishes. And so this is kind of very much like what Reichardt and Schultz do. But what is somewhat different is that when we introduce the new prime, Pn plus 1, we need a plan for Pn plus 1. And what I mean by a plan is a map homomorphism from the GQ Pn plus 1 to G. That is to say, I have to figure out in advance the decomposition group of Pn plus 1, how it's going to map to G. So it's a sort of a slightly complicated situation. That is to say, we do this lift one level at a time. Each time we do the lift, we introduce a new prime, but when we introduce the new prime, we figure out for that prime what the lift looks like all the way till the end. And of course, what we then need to do when we introduce these classes in H1, which, as it were, correct our naive lifting of F, is we have to make sure that all the primes that we're already using remain on plan. That is to say, for each of those primes, we know what the lift to P looks like. So we know what the lift to P mod Pn plus 1 should look like. And in general, it won't be that. And so we have to correct the lifting to make sure that at each prime, we are on plan for all previous primes. So when we introduce the new prime, Pn plus 1, part of what that prime is supposed to do is to allow us to make sure that all the lifts for previous primes remain on plan. That's what I'll say about this strategy of the proof. Okay, and so the result is the following theorem. If G is stably inertially generated, then it is a Galois group. Over Q. Okay, now how does this fit in with what I said about interesting examples of pro-P groups G? When can we expect these groups to be stably inertially generated? Okay, so let's talk about the case that I think of as which I find personally most interesting. So let's talk about p-adic analytic groups. So a p-adic analytic group has a Lie algebra. So a p-adic analytic group is attached to a Lie algebra, I don't know, L, which is a QP Lie algebra. And so what we need if we hope to be stably inertially generated, so a necessary condition, which in fact turns out to be necessary and sufficient, well, a necessary condition, let's say, for a p-adic analytic group to be stably inertially generated is that L is spanned by inertial elements. So, I mean, you can perhaps guess sort of by going from the group theory ideas to sort of the usual way you go from group theory picture to a Lie algebra picture. You want a commutator of x and y to be a power of y. That's like in Lie algebra terms, saying that the bracket of two Lie algebra elements is a multiple of the second one. So let me give a definition. So definition, y is inertial if and only if there exists x in the Lie algebra such that the bracket of x and y is equal to some multiple of a not equal to 0. So an example of this, of course, is what happens if y equals E or F and x is equal to H in an SL2 triple. so the Lie algebra SL2 is spanned by inertial elements. Namely the conjugacy class of, the conjugacy class of, let's call it 0, 1, 0, 0, spans SL2. And more generally, if you have a split simple Lie algebra, that you can make this trick work. And in fact, it's more general than that. So let me make a precise statement in terms of Lie algebras over p-adic fields. So let me say the following. For definition, a simple Lie algebra L over QP is anisotropic if it has no non-trivial inertial element. Well, the word anisotropic has been used in this theory before, and the theorem is that anisotropic, as I'm using it, corresponds to anisotropic as it's been used before. And so what that means, so let me say this. So if G over QP, this is now a different sense of G, maybe I'll underline it to indicate that it's an algebraic group, is a simple algebraic group then the Lie algebra of the QP points of G is anisotropic if and only if the rank over QP of G is equal to 0. That is to say, if there are no split tori, even of rank 1, inside G. And the theorem, which comes from the classification of simple algebraic groups over QP, is the following. Let's put it this way, the only simple algebraic groups over QP which are anisotropic, or which are of rank 0, are those of the form SL1 of D, where D is a division algebra. With center QP, right? So if you think about so what is SL1 of D? It means the kernel of the reduced norm map from the multiplicative group of D to QP star. So this is reduced norm is like the determinant. I mean, this is a twisted form of, if D is an n squared dimensional division algebra, then SL1D is a twisted form of SLN of QP, but it's an anisotropic twisted form. So all other simple algebraic groups are not anisotropic, which means, so the corollary of all this is if L is a simple Lie algebra over QP, not of the form SL1 of D for any division algebra. So this SL1 of D, to be clear, is the Lie algebra of the group SL1 of D, and it consists of elements in D whose reduced trace is 0. So if L is not of that form, then the inverse Galois problem for L has a positive answer. I have to explain what this means. So what should the inverse Galois problem for Lie algebras mean? A Lie algebra is associated not with a single, in this case, it's a p-adic Lie algebra. It's not a single p-adic Lie group, but it's a whole family of p-adic Lie groups, which are all commensurable with each other. We sort of think of it as being kind of a limit of smaller and smaller neighborhoods in a p-adic Lie algebra. So it seems reasonable to define the inverse Galois problem in the following way. So I'll call it definition. The inverse Galois problem for a Lie algebra, a QP Lie algebra L means does every p-adic analytic group G with Lie algebra L have arbitrarily small open subgroups for which are Galois groups over Q. Okay, and so the theorem would therefore be that yeah, I mean, I stated the theorem before I stated the definition. If you have a simple Lie algebra which is not of the form over QP, which is not of the form SL1D, then you get a positive answer. And this brings me now to the question: does the inverse Galois problem for SL1D have a positive solution as well? To be clear, if we restrict ourselves to tamely ramified extensions, then by what I've shown so far, the answer is no. On the other hand, you're obviously tying your hands if you're, if you're trying to realize like SL1 of D, if you're trying to realize that as a Galois group over Q, and you don't allow P ramification, like P inertia, that seems like you're really tying your hands. And in fact, it seems pretty clear that traditional Galois representation methods, you should be able to construct, like, I don't know, an abelian variety with an endomorphism ring, which is an order in a division algebra. You could do some construction like this to get a Galois representation, which will be a p-adic Galois representation whose image will be some open subgroup in SL1D. But the way that I formulated the inverse Galois problem for Lie algebras is not just that there is some p-adic analytic group with a specified Lie algebra, which can be realized as a Galois group over Q, but that there are arbitrarily small ones. And there, it's not clear to me that Galois representation methods offer much hope. I just don't know what to expect in this case. Another class of questions has to do with, okay, so let me mention the following theorem. This is sort of special, but it suggests kind of a direction where, I mean, I'm going to state a result for SLN, but it seems pretty clear that the same kind of thing should work for other split groups and maybe even somewhat beyond split groups. Okay, so here's the theorem. So let A be a complete Noetherian local ring. Maybe I'll write down the ideal. Let SLN1 of A be the kernel of the homomorphism from SLN A to SLN of the residue field. Then SLN1A is a Galois group over Q. So how much can this be generalized? I don't know, but probably to a considerable extent. And this includes, of course, so this includes the case that I called 3 before. It includes the case of power series in one variable over FP. And now what about other kinds of just infinite pro-P groups? So question, are there other just infinite pro-P groups, which are Galois groups? Over Q, to be concrete, the Nottingham group. It certainly has a lot of inertial elements, but I don't think it has enough to satisfy the hypotheses of our theorem. At least we looked at this group and we were not able to make it work. This leads to a kind of more general question, so this will be the last question I ask. Can we improve the method proof to get by with fewer inertial elements? And I want inertial elements in every PM, which span PM mod PM minus 1. The way that the proof works, we plan one step in advance for lifting. And it seems to me that if you didn't know that every step inertial elements are available, but you wanted to plan several steps in advance to get to the next round of where you have inertial elements, the kind of like global duality methods that we use to show that we can plan one step at a time probably don't apply. I mean, you might end up doing somehow looking at non-abelian cohomology groups rather than abelian cohomology groups. Anyway, we couldn't figure out how to plan more than one lifting step in advance to make sure that we wouldn't encounter obstructions until you're in a position to then move your representation again to plan for the next round. So that's a question which I think is attractive, but I spent a little bit of time on it. I haven't succeeded with it at all. And I think I will stop there.